Hello, everyone. Last week, we started our description of TCP. We've seen that TCP requires a sliding window, requires the receiver to have a resequencing buffer, and the sender to manage the sliding window. Because of that, there must be a connection between the source and the destination. And this is traditionally, not always, but this is traditionally done by sending a SYN packet followed by SYN ACK and an ACK. This is in theory. In practice, how is it done as a programmer? Remember, the goal of the transport layer is to provide a programming interface. So this is how this is done, similar to the UDP sockets. On the client side, here I'm showing a Python version, which avoids many of the low-level details. So we create a socket, and then we simply connect to the destination. So the destination must be given in the form of an IP address and a port number. Of course, the source here on the left, the client has a port number, but this is a temporary port number that has no meaning. So if we don't care about the port number, we let the operating system associate it with the socket, but the socket always comes with a port number. On the server side, like for UDP, typically a server wants to specify a given port number because servers need to have, in principle, a well-known port number. So it will, in this case, that's the number chosen by this socket here. Then there is something specific to TCP. Here it's called the listen. The listen call here means create a queue for receiving the SYN packets. The SYN packets, in principle, we'll see some exception, in principle contain no information. So this is just for managing the incoming connections. And then this server code, after creating this queue, does an accept. So an accept means read, or more precisely, consume one SYN packet from the queue. If there is one, if there is none, it will be by default a blocking call. The server will wait until a SYN packet arrives. And when the SYN packet arrives, this call unblocks the socket, the program that that issued this the call here, which is illustrated by the dotted line here. And this accept, when it's executed, will have the effect of sending the SYN ACK and also receiving the ACK here. The return code here of the accept is con. It's not a single code like an error code here. It is a connection. It is a socket here. So one very specific thing to TCP is that when we start a TCP connection, we create a new socket. The socket is forked from the previous one, which means it inherits all the port numbers. It inherits the local port number of the socket here. So we have S1, which is the socket which is used by the server to receive the connection requests, the SYN packets. As soon as one connection request, one SYN packet is consumed, another socket is created, and it is on this other socket that we can do useful work, that we can do send or here receive information here. So this ping thing means it is a different socket here. Why do we do this? Well, because most of the time, we don't do what I just shown, but rather this one here. A server will typically fork parallel threads to execute, to treat the different TCP connections here. So there will be as many sockets as there are TCP connections that are being processed here. Observe something that here, all those sockets, there is the first socket, which is called the non-connected socket. It's non-connected in the sense it's just a local queue. There is no association with a remote entity. But to do something useful, we fork another socket, which is then connected. Each of those ping sockets here is connected to a given destination, a given remote system. So it's associated with a local port number and a local IP address, and a remote port number and a remote IP address. And in principle, two different sockets here cannot have the same association. You cannot have two sockets that are connected to the same local port and IP address and the same remote and IP addresses. But you can have multiple sockets that are bound to the same local port. S1, like each of the ping sockets, is bound to the port, in this case, 5003, which is the server port. And this is motivated by the idea that a server typically, unlike perhaps a simple UDP interaction where a server handles one message and immediately answers here we expect that there might be a long interaction. For example, there might be transfer of objects if those are HTTP, if the application is using HTTP. Here is how the operating system views the sockets here. Here I'm showing for IPv4 sockets. I'm not showing a dual stack socket, which would be an IPv6 socket that's able to accept IPv4 packets that exist in exactly the same way we saw last week about UDP. But here I'm illustrating, for example, in the IPv4 part of this operating system, how the SYN packets will go to the buffer that is associated with the listen call. And once a listen call has been done, multiple sockets are created, and the data is delivered by the operating system to the socket, to the appropriate socket, by looking at the source and destination port numbers, and also possibly IP addresses here. One special thing of TCP sockets is that TCP offers a stream service. In particular, it is TCP, not the application, that segments the data. So when you do a socket call by doing, for example, what is shown here, send, we don't do send to because the socket is connected. We can send only to one specific system. Here I'm showing send on the left and receive on the right, but typically a server will receive some information and will reply. So there will be send and receive on both sides here. What was I saying? Yes, here when we do this send message, here I'm showing that a packet is sent, but this may or may not be true. It is probably true for the first send that is issued by this application. But if this application does 5 sends one after the other, perhaps at the second send, the operating system will decide, well, I've just sent a packet, so this guy seems to be sending lots of packets. If the information is small compared to the size of an IP packet, the operating system may decide to wait a bit and create larger packets. In particular, what might very well happen is that while the operating system is busy serving the first send, the application creates another send, but the first send has not yet been sent. Then in that case, it is possible that the creation of the IP packets will be done later after the send. This is typically what is done by what is called TCP segmentation offloading. Modern data center computers will do the decision of packing the data into IP packets only on the communication adapter. So well after the application has done the send and completed the send here. So this is allowed because it is TCP, not the application, that chooses how to segment data. Segment data means how to create TCP packets with the data. Of course, if you create a send that is exactly the size, the maximum size that would fit in an IP packet, then there's no choice. TCP will create exactly packet. That's a rare event that happens very little. Typically, the block will be larger or smaller. If it's larger, TCP will need to create several packets. And perhaps the last packet is not a full packet. So perhaps TCP will wait a bit to put the beginning of the next block that you write into this packet. Another rule is that with TCP, segments should not be fragmented at the source. That's in contrast with UDP. In UDP, we saw that UDP has a message semantic. UDP says, if you call and send one block, I will deliver to the destination exactly the block with the same boundaries here. And I allow a block that is larger than an IP packet up to some maximum limit. And if necessary, the IP layer will break it into several IP packets. With TCP, we never want to do that. We will discuss more about fragmentation a bit later. So the TCP segment should not be fragmented at the source. And typically at the beginning of a TCP connection, there is what is called a negotiation of a maximum segment size, which is the maximum size that is supported at least by the client and the server. The maximum segment size is very small for IPv4 packets and is much larger for IPv6 packets. So we will see lots of small IPv4 packets because of the default of TCP maximum segment size. So one side effect is the segmentation. The other side effect is that on the receiver side, as we have seen last week, data accumulates, and there can be, in particular, what is called head-of-the-line blocking. If one packet sent by the sender is lost, then, but if it's an isolated loss, all the subsequent packets that may have been received by TCP will not be available to the application. They are probably present in the socket receive buffer, but the application will not be able to consume them. So the delivery of this packet is delayed, which means the delay perceived by the application is increased by the loss of a packet here. Right. For which types of applications do you think that such a behavior would be a drawback? The Zoom poll is open. Should be open. Do you see a Zoom poll on your? Oh, sorry. Speak up poll. Yes. I see. Yeah, we don't do Zoom polls this year. We're all happy to be in class, most of us. I close the poll in a few seconds. Closing, closed. The majority says C, which is, well, there's probably not a single good answer, but probably the ones I'm circling are valid answers. HTTP1, that's the historic version of HTTP. When the web was created, it used one TCP application per object. Yes? Well, an object in a web page. You go to a web page. Back at that time, when the web was created, there was no object on a web page. It was just an HTML file. But it was also possible to embed images like a logo. And now you have flash players and all that kind of stuff. So scripts, images, sounds, etc. They're all are different objects that are linked by the HTML code that you have when you download the web page. And the original version of HTTP was as simple as possible. And in fact, the web emerged because it was possible to do it in a very simple way. It simply created one TCP connection for every object. So you would go to the server, get the HTML file. When you inside the HTML file, you see a link to someone else, you would open another connection. And that allowed those transfers to happen in parallel. And if there was a message, a packet lost on one object, then it would not prevent the others from downloading. Yes? Each connection that were open for each object, where the object is different for. As each object port that identifies the object, or is there only one port? So the question is, when a web client goes to a web server and decides to open multiple connections, for example, to transfer the first link it sees, it will open a new connection by doing a new socket call, will create a new socket, will receive a new local port number. but will connect to the same final destination port number. It will be another source port number. Exactly. Yeah. So you will do as many transfers and as many. So this forking of connection is only on the server side. When we fork from a connection request, that you get a new connection number, but not in this case. So this gave very good performance from the viewpoint of avoiding the head of the line blocking, but it has a drawback. It makes a lot of load on the server side, and the server has to manage a large number of connections. So there is very quickly an optimization. It was HTTP2 that had one TCP per web page. So when you transfer an object from a link that is in your web page, you reuse the same connection and send simply another HTTP message to get that object. Of course, while doing that, you have the head of the line blocking. If you're busy downloading the logo, or worse, a music that is completely useless but is still present, and the music file is not yet downloaded, then you cannot send the request for the next object. So that delays dramatically the transfer time. This is why HTTP2 has implemented a number of mechanisms for what is called multiplexing, allowing to send fractions of an object to allow to still go on. So the complexity has been pushed inside HTTP to handle the head of the line blocking. We will see in a few more weeks a more radical answer to that, which is called QUIC. QUIC is trying to have the same behavior as HTTP1, but without the complexity in terms of connections. We'll come back to that in a few more weeks here. Certainly, a drawback is for real-time applications. Imagine you have a sensor that sends every 1 millisecond a status, and then you control it with a controller. If you send that over TCP, if a message is lost, the TCP connection will insist on repairing the loss of the previous measurement before delivering the next one. But if you're controlling the machine, if there is a next one that was issued, that's the one you care about. So you want to react to an out of bounds of some temperature, some pressure, etc. So this is completely useless for such applications. So such applications would typically use UDP. They cannot use TCP. TCP is useless for them. So they have to use UDP, which means they have to use also their own reliability mechanisms. We'll see, for example, that there are applications for real-time video streaming. An example of real-time application is also video. If you do interactive video and you want to have end-to-end delay that is, let's say, larger than 100 milliseconds, that's for the very high-quality interactive video. If you do gaming, you want even less delay than that, then you will have problems with TCP here. You have to do it with your own UDP. Another small question. Another small question on speak up. I close the poll in a few seconds. Closing. Of course, the answer is A. Not just sending or receive are possible on both sides, but the server is the one that will have this listen queue, this non-connected socket. So we see that contrary perhaps to UDP, the server and client roles in TCP are very distinct. There is there are large differences on both sides. I'll skip this and I'll come back to the things, what I call bells and whistles. So what we've seen is, I would say, a fraction of the first half of the story about TCP. The second half we will see when we talk about congestion control, because TCP is also used to perform congestion control, regardless of the transport layer function. It's another function that's added to TCP. But already to do its transport layer function, TCP requires a number of other bells and whistles. Bells and whistles are optimization. So TCP is probably the protocol that has been more worked upon. If you look at the number of papers, RFCs are the internet official architecture documents. There's a huge number that has to do with TCP and what is now called QUIC. Not surprisingly, because that's the core of everything we do when we use the web all the time. The performance of TCP impacts our perceived performance of the interaction through the web. A number of things that TCP needs to do is, for example, when to send a packet. I have mentioned the fact that TCP has the choice to decide whether, when I do send call through the socket interface, should I, now imagine your job is to code TCP, or perhaps do, which is an unlikely job because it has been done so many times, but perhaps you will be working on a system on a chip that has to implement some version of TCP. When do you create a packet here? So here you have conflicting requirements. You want to have as fast a response as possible. You don't want to delay if the application writes something. Why should you wait? So you don't want to wait. On the other hand, if you have an interactive application that does writes 1 byte at a time, you can easily write such an application using sockets. If you have a file to transfer that is 1 million bytes, you can do a loop that says read the file, read the 1 byte, write it into the socket, read, write, etc. You can do that. So if you do that, you will write into the socket 1 byte at a time, which is, after all, the simplest way for the programmer's viewpoint to do it. And some applications do that. For example, when you have an SSH interactive window, when you type on your keyboard and you see on the screen the characters that are being typed, in fact, the characters are echoed by the server. So your machine is in fact sending 1 character at a time, and the server is echoing them back on your server. So for such applications, the question really is asked. I mean, you don't want to create, for efficiency, you don't want to create 1 IP packet for every character. So latency versus efficiency, how do you do that? There is a lot of heuristics, and by default, there's Nagel's algorithm that will accept to write small packets. But if you have more than 1 very small packet that is unacknowledged, then you will wait a bit until at least filling half a maximum packet size. So those are such heuristics. That all of those heuristics can be disabled by socket options. This is why there are hundreds of possible socket options on a TCP socket. But by default, this is enabled. Similar to when to send a packet, there's the same question about when to send an ACK. We've seen that an ACK can be sent whenever something happens, but if you have nothing to send back, if you have two-way communication, you receive a packet. Should you send an ACK now, given that if there is two-way communication, perhaps in 1 millisecond, this application will respond something to the source. So you might put the ACK field in the response instead of creating an empty packet that sends an ACK. So there are similar algorithms to do the balance between efficiency versus latency here. And there are other beyond these algorithms. I mentioned the TCP offload mechanism. You can also have hardware solutions that will try to do those things on the communication adapter here. When to increase the window size, we've seen also that the window, this is more subtle, the window size is supposed to reflect the available buffer size at the receiver. And we've seen that this is how we prevent a stupid case of losing a packet at destination because the socket buffer is full. So we advertise the window. But there are bizarre cases that can cause what is called the silly window syndrome avoidance. That would be the case of an application that sends data 1 byte at a time, and the window, the buffer, there's 1 byte free in the buffer at destination. Then if you are just greedy, the destination could send a window advertisement of 1 byte that will allow the source to send 1 more byte. And then this byte will be consumed. As soon as 1 byte is consumed, you can send a window advertisement of 1 byte. I said if you have an application that writes 1 byte at a time, that's not correct. What I should have said is if there is a receiver that consumes the data 1 byte at a time. This is exactly what could happen. That's the dual of this here. When there's an application that might create 1 byte packets, here you might have application that creates 1 byte free space in the receive buffer. Obviously, if you send a window update of 1 byte, you will force the source to send 1 byte at a time, which might also not be efficient. Perhaps the source has 1,000 bytes to send, and it's better to wait anyhow for this to happen. So there is a similar to Nagel's algorithm, the silly window syndrome avoidance. And then there are 3 more detailed things, 3 things that we'll look in detail: how to detect packet loss, how to choose initial sequence number with SYN cookies, and how to avoid also the 3-way handshake. So there are some of the optimizations that are present in most versions of TCPs, and the ones you probably have in your smartphone, in your computer, and the one we will have in the lab. Before getting there, let me ask you a question. Here I'm showing a scenario that we saw last week where 2 packets are lost here. And of course, TCP will send an acknowledgement here. TCP replies with an acknowledgement as soon as it receives 1 packet of information, and it replies with a block, SAC block here. Now, at point 7, the receiver knows that, or can infer that something was lost because it receives an acknowledgement with a gap. So I know the source knows it has sent packets 1, 3, 4, 5, and receives an acknowledgement for packets only 1 and 5. So is it a good idea to declare a packet lost and retransmit? If you have to code your own version of TCP in Linux or whatever, would you declare a loss and Bing resend the packet? I close the poll in a few seconds. Closing. Here, majority says B, but this is one of those rare quizzes that I send where the correct answer is I don't know, or everything is true. Well, all of this is possible. The truth is we don't know. And that's the problem, in fact, when we do distributed systems, we cannot have the global state. We have to infer locally from what has happened. So A is possible. And it is very frequent, probably. Most of the times, we would be in cases like this. But it could also be that the ACK has been lost. Sorry, this could not be true, correct, because we have the ACK here. But it could be also that those packets are simply a bit delayed. Perhaps they will arrive a microsecond later. And the receiver, which is a busy server, does what it can, so we cannot be true. Note that whatever you do, there will be no harm. There will be no protocol error, in the sense that if you have a duplicate packet, TCP will not crash. You will simply know, oh, because there is a sequence number in the packets, TCP will know, oh, this packet is out of bound, I have already been delivered, so I simply discard it. It will know it's a duplicate. So if you resend a packet that has been received, there is no harm. Fortunately, otherwise the job of TCP sender would be very difficult. You would need to be extremely conservative. Before sending something, you must be sure that it has truly been lost, which is as hard as knowing that it has been received. So, of course, we must accept the fact that the packet is duplicate. That's a side effect of not being sure that it has truly been lost. So all of this is possible. And this is reflected in what most versions of TCP today do, which is called fast retransmit. So we mitigate answers A and B by saying, when I receive a SAC block that indicates there is a gap in the packets that have been received, I don't react immediately, but I will react if that happens more than 3 times, for example. The default in many systems is 3, tends to become smaller now, but many systems have this value here. So that means here, 3 means 3 duplicates. Let's see an example. So the time is now flowing vertically. Packet P1 is sent, P2 is sent, P3 is sent, and the source continues sending. So the acknowledgements that will be received by the source are triggered by packet 2, 3, 4, 5. Here, we see that we will receive an ACK field followed by a gap given by the SAC here. And it is only after receiving in this, if the value here of max number of max duplicate ACKs is 3, it is after receiving 3, what is called duplicate ACKs, that we will say, now I think there is a loss. So this is a variable you can change on easily on any Linux or Windows systems. Here, duplicate means packet 4, the first ACK here, 2000, corresponds to packet 2. So I receive the ACK. This is not a duplicate ACK. Now, when I receive packet 4, I receive an ACK, where remember the ACK field in TCP is ACKing everything cumulatively up to this number. So that's the second time I receive a packet with such an ACK number. So it's a first duplicate. Now that's the third time, so it's the second duplicate. That's the third duplicate. My value is 3, so after 3 duplicates, I retransmit. So I retransmit the first packet in the gap, or remember, if there's more than 1 packet and the maximum segment size allows, I might put more than 1 packets in the retransmission. Here the source retransmits P3, and then the acknowledgement that will be sent here will be, by the way, 6000. So this is according to some measurements that were done by companies like Google in particular, this is the most widespread way of detecting losses in TCP. So most losses are detected by this heuristic. Of course, this heuristic is not sufficient. Fast retransmit detects most losses, but not all. Why? Well, because as a heuristic, it's not perfect. But certainly, there's an obvious cases. If the number of max duplicates is 3, and if the loss was towards the end of the transmission, perhaps there will never be 3 more packets to transmit after the loss. So there will never be 3 duplicates, though there is a loss. Also, there might be a burst of losses. For example, the line is broken during 1 millisecond, then there is a fast recovery mechanism that reinstalls the lines or reboots the modem or whatever. So it might be a transient failure, in which case everything is lost. Then, of course, there will be no duplicate ACKs because there will be no ACKs at all. Right? So this is not sufficient. Of course, TCP, like I showed last week, always use a retransmit timer. In distributed systems, that tends to be the last resort function, that to detect whether things go wrong, you start a timer, and when it expires, you re-examine what has happened. So for every block of data that is sent, there is a timer. So you can imagine the TCP code is fairly complex. For every block that has been sent on the sender side, there is an associated timer. And when this timer expires, then this data is retransmitted. When a timer expires, worse than that, there's a further heuristic that most versions of TCP will consider that because I have other heuristics to detect losses, when a timer expires, it is something bad that has happened. So typically, when we do that, we declare that there's a severe loss, loss of channel, for example. All timers are reset and all data is marked as needing retransmission. So all the timers that are following the data, in particular, are reset, which will avoid that if you lose block 2, for example, then perhaps 1 microsecond later, block 3 timer will expire, block 4, etc. So you will create a burst of retransmissions. In that case, you will not do that. You will retransmit only the first block that has expired. For the other, you have reset the timers, so they will expire much later. Another thing that TCP must do is to set the timer right. How to set the timer right? Well, that's very easy if you have a static system. If you're designing, for example, the communication network of a car, you know the round-trip times between the thousands of computers that are in a car. You know that their transmission round-trip time is perhaps order of 20 microseconds. So you can set the timer to 20 microseconds. In the internet, if you go to a website that might be in New Zealand or might be here at EPFL, the round-trip times are radically different. Also, the round-trip time depends on how busy the servers are. If you go to a congested server, the round-trip time might be very large, simply because your server has a huge queue and is very busy processing a large number of people like you. So the round-trip time needs to be estimated for the retransmission timeout. We said when a packet is transmitted, we set up a timer. Then we also set up we need to estimate a value here, and the value ideally should be an epsilon larger than the round-trip time. This is performed by TCP using a value that is called RTO, round-trip, an estimate of the round-trip time for the retransmit timer that uses a small filter that is given here. This filter is simply done in this very simplistic way. It uses in particular absolute value rather than square root of a standard deviation. I will illustrate on a figure how it works. It is simply recording for every block of data that is received how much time elapses until I receive an acknowledgement. So for every block of data that TCP sends, it starts a timer, but it also records at what time it is sent, and whenever the ACK that acknowledges this block is received, it will record this. Of course, with safeguards, you have to see if there is a gap, an ACK with a SAC. You need to be careful and perhaps not consider them. So there are safeguards to make sure you're really monitoring the round-trip time and not the time including retransmissions. So whenever an estimate of the round-trip time is available, we pass that into the filter, and this filter computes an estimate of the variance of the variability and adds a fraction of the variability to obtain the timer value. So here I'm showing on this simplistic simulation the values of the round-trip time as measured by successive TCP packet transmissions. And in pink, you have the value of the round-trip time of the timer value. It starts by 6 seconds for many. This is a standard default for many systems. So you want a very safe upper bound on the very, very worst case that could ever happen in any system in the world here. And then this filter, if here I'm showing there is a small variability of the round-trip time, it will quickly converge to the true value plus a bound, and the bound reflects the variability that is here. Here, during this period, the round-trip time is hypothetically constant, is equal to the same value, then the filter converges to this true value. As soon as there's some variability, positive or negative, it increases or decreases. This results in the bound being amplified here. So TCP sender will do this and will make sure that with very large probability, the RTO will always be larger than the round-trip time and not much larger. So that if you're in a smooth case like here, you have a very good estimate that allows you to time out exactly when necessary. When necessary is a bit after the round-trip time. If you time out too early, it is like having a wrong heuristic of fast retransmit. You will resend packet unnecessarily. There will be other side effect. The timeout causes sudden decrease of the sending rate. We'll see that when we talk about congestion control. So hopefully most of the time, it will be like here, where the ping value is above the true value here. So we've seen the timeout, we've seen fast retransmit. When do you think that fast retransmit might fail? I close the poll in a few seconds. Closing. You see that the majority says C, which is probably true. Here we're in an area where things are not black and white. But answer D asks an interesting question. How about packet reordering? If there is massive reordering in the internet, fast retransmit will often be wrong. Right? If packets can be shuffled and have very large reordering, then it may happen that you have a gap in the acknowledgement simply because packet 2, 3, 4 were faster than packet 1. And then, so that would often fail. And it's true. Now, because of that, probably, because fast retransmit was done very early in the evolution of TCP, there is a requirement on the internet that you try as very hard to never reorder packets of the same TCP connection. Although TCP has a job of reordering things, we say, paradoxically, because we assumed somewhere when we did fast retransmit, perhaps, that the reordering must not occur a lot. So now we say routers in particular should not try to avoid that. We'll talk about OSPF last week. In the internet, there are lots of parallel paths that can, because for reliability and throughput, we're happy in a network with our parallel paths to use them all together. Parallel paths might cause reordering, because if you send 10 packets on 2 different paths, you can never guarantee that they will arrive in exactly the order you sent them. So those equal cost multipath routing in the internet will invariably have the constraint that try not to do that for packets of the same connection. So you will try to have techniques that we'll discuss next week to make sure that all the packets that have the same TCP connection should be on the same path. So this is something that will probably not happen. But it's true that if your packet is the last one or one of the very last one, then there is no following acknowledgement to detect, so fast retransmit will fail. Because of that, there is an additional, in the millions of, not millions, hundreds of bells and whistles of TCP, there's another additional algorithm called Taylor's probe that tries to avoid this by having another timeout, the PTO, the probe timeout, and when it expires, a probe segment is sent, which is a retransmission of a non-ACT packet, anticipated if you want. So fast retransmit did not say anything. Timeout, the regular timeout did not say anything. So we have a smaller timeout, and then we'll be conservative, we'll retransmit, but we'll try to retransmit just the minimum amounts that can be retransmitted. And if that was truly a last packet, then this will trigger new ACKs and might trigger fast retransmit. I mentioned packet reordering. I mentioned that it's rare on the internet. Still, inside machines, it's not rare. So when the switching fabric of a router, which is here for backbone routers at extremely high speed, is highly optimized and at lots of parallel paths. So switching fabrics might, for some of them, be non-packet ordering. So there might be a difference in timing, but those differences are minuscule because the switch fabric is very fast. So we're talking of differences in orders of microseconds. So for that, there is another complement to fast retransmit, or something that replaces fast retransmit, is not so much deployed, but might be more in the future, which is called RAC, recent ACK, that tries to detect that. It detects if there is a gap. It also analyzes the timing. If this gap is for packets that were sent close together at about the same time, the sender knows that because it timestamps all the packets sending, then we'll say perhaps it's reordering. If that happens with a timeout, with a difference in timing which is larger, I will say, no, this is not reordering, it must be retransmission. So this is another alternative or complement, improvement to fast retransmit. The next improvement we will discuss is SYN cookies. So what are SYN cookies? Well, SYN cookies will be revealed after the break. So we do a break of 15 minutes and we start at 1:15. Back to SYN cookies. SYN cookies is an answer to an attack that was mounted a few about 10 years ago. Imagine you take control of, you infect a computer, and the program that infects your computer decides to send a lot of SYN packets to a given target, to a server. Of course, the infected computer has no intention of answering those TCP connections. In the worst case, might not be able to do this if the network from which you're sending doesn't do what is called reverse path checking, sends it from an invalid source address. But even if the source address is valid, there is no intention to do that. So why is it a powerful attack? Well, because the SYN packet, when it's received by a computer, requires the computer to do a lot of resource reservation. You have to create a socket buffer. You have to start all the machinery. You reserve some kernel space, 4K, and you will keep it. Of course, there will be a timeout. If the SYN packet is not followed by any decent activity, then you will consider, well, this is an aborted TCP connection. We'll release the resources. But the timeout, as usual, is hard to decide here. The timeout is typically order of many seconds, because perhaps somebody is truly trying to connect to the server over a cellular connection with your smartphone. You're in the mountain, your connection speed is very, very low, so you send the SYN packet. The server sends to you with the SYN ACK packet, but the SYN ACK packet is lost. You time out, you resend it. All of those interactions might take seconds, many seconds, even around 10 seconds or more. So the timeout value is necessarily large. So that means that if you're able to inject to a server thousands of SYN packets per second, then the server will simply be busy creating all those TCP socket buffers for things that don't exist. So that's a multiplication of a denial of service attack, where not only you send a lot of packet to a server, which is per se a denial of service attack, but you send packets that force the server to create a lot of work and reserve a lot of resources. So that's the dream of an attacker. This is mitigated by what is called SYN cookies. So what is the solution? Well, the solution is very typical of some things we may want to do for security or efficiency reasons. We can always trade state information versus cryptographic means that are sent on the fly. What I mean by that is, if I have to keep state information, which is the case of a TCP server, when I receive a SYN packet, I have to remember what is the information that's in the SYN packet, like the initial sequence number, typically other things sent in options, like the maximum packet size, and I need to create a socket and store all this information. There's an alternative way to that. If you don't want to store information, you can send it in a cookie. Right? Of course, the cookie must be, so what is a cookie? A cookie is typically the information that you want to send authenticated. So you send it back to the other end, and the other end will give you that information back. Now, because you've authenticated it, the information that you receive, you can make sure it is truly the information that you should have stored, but you did not store. So if you send me something that I should remember, what I can do is I hash what you send to me with a secret that I will, that is not a secret specific to you, but a secret that is machine-wide. I hash everything and I send it back to you. When I need the state information through an interaction with you, you send me back this cookie. I can verify, because I know the secret, I can verify with a hash that it is a non-forged secret. So I will assume that this is the information that is relative to our interaction. So that's a common trick that is used in SYN cookie. This can be used in lots of other settings for avoiding that a server keeps state information when there will be future interaction. So specifically here, the SYN cookie is as follows. When the server that implements SYN cookies receives a SYN packet, it will encode, it will put the cookie in the sequence number for the return direction. So that is a piggybacking of something that was not intentional. Remember that TCP allows two connections of information, and the two connections can have their own sequence numbers. So here we don't use a random sequence number. Instead, the sequence number encodes a timestamp that is kept by this server. The information, the useful information that was in the SYN packet, which is Do you hear me now? Yes, okay. Good. So the hash that I mentioned before, the cookie that is sent back is in fact in the form of the sequence number to be used for the reverse connection here. Now, if the source is legitimate and was intending to open a TCP connection with the server, the protocol says we ACK this SYN ACK by incrementing by 1 the field here. So in some sense, we are returning the cookie back to the server. So the server will decrement by 1 the ACK field, will verify that this corresponds to the secret that was hashed. And if that happens, then the server can only now create the socket, which means that the server will commit the resources associated with this TCP connection only when the SYN ACK, when the ACK here is received by the server. Which means that if you were mounting this attack against the server, you will need to not just have something that floods a number of SYN packets, you will need to have something that's able to respond to the SYN packet, which is much more work and will also be much easier to detect because you will see some activity on the client side. Question? You mean you could do it only after? Yeah, I could. Like, I did that. I don't only send SYN packets, but I also send the first notification line, right? ACK equals 5+1 also. Because it's at the first communication that the resource are allocated on the server side, right? To complete the handshake and make the server allocate. Yeah, but if you complete the handshake, you must somehow remember that you completed it. Right? But we can discuss that. Perhaps there are optimization to SYN cookies that are possible. So this is the optimization that was done. So the result is that if the SYN was bogus, then no ACK follows and the damage is reduced to loss of computing power. So there is still damage, but the damage is lost to, consists in having simply computation here. Now, a small question. If we have a server that does not, so SYN cookies is implemented in many, many servers today because the attacks are so dominant. I mean, if you're curious and if you open a server at home by opening the server ports on your ADSL modem and you do Wireshark, you will see that a few seconds after opening the server port, you will be attacked by lots of things. So there will be port scans, there will be all kinds of things. So the internet is like nature. In nature, there's lots of virus and insects and so on that are always trying to destroy or take advantage of existing life. Here is the same on the internet. So, of course, the SYN cookies are almost necessary. Now, assume you have a server that for some reason does not implement SYN cookies, and the ACK here, the number 3, is lost. After all, the ACK is a packet. Like any packet, it can be lost. What will happen in this case? I close the poll in a few seconds. Closing. And the majority says B, which is correct, but A is also correct, which means that the correct answer is C. So this ACK can be lost like any packet. And the ACK is ACKing the SYN ACK. So when I send a SYN ACK, it's like any packet that I'm sending, in fact, I am forced to do everything we do to repair packet losses. This is why the ACK here is as if there would be one byte. If you see the ACK of a SYN packet always does as if the SYN packet contained 1 byte of information. Why they do that is probably to force the programmers who implements this to remember this is a packet that must be verified. We must make sure we receive an ACK for this packet. When we send an empty packet, which just contains ACK, we don't verify that it's received. So we don't set a timer because there's no block of data associated with it. So here a SYN packet is handled as if it contained 1 byte of information, though it contains no information in most cases. So here, when this packet is sent, if no ACK comes, then there will be, it will be retransmitted, probably after a timeout, because fast retransmit will not, of course, allow us. See. And also, we need to keep state information because we don't implement SYN cookies, so the state information was created here and will be kept until the timeout occurs. So this is what SYN cookies will save us from. If the server, in contrast, implements SYN cookies, then this will not happen, which has a small side effect. The side effect is that this packet here is not sent reliably. So if this packet gets lost here, then it will be lost, and nobody will detect the loss. Correct? Question?
But doesn't the state information get destroyed once the timeout, the SYN ACK timeout occurs?
The question is, doesn't the state information get destroyed when the SYN ACK timeout occurs? Yes. The answer is yes. No, you will destroy it. No, you will keep the state information until, no, not the SYN ACK timeout, another timeout, which is the timeout for the lifetime of a TCP connection. There's still a side effect. If you implement SYN cookies, you will not do that, because when you send this one here, you go to sleep. You forget about this connection. That's the goal of SYN cookies. You receive a SYN, you reply, and you forget about it. If one day the SYN ACK comes back, if one day, sorry, the ACK comes back, then you know it was a true connection. But if this packet doesn't come back, the connection will fail here. And since this packet here is not sent reliably, you might have a deadlock. You will have a deadlock only in the case where the source does nothing after that. So if the source sends, after sending the ACK, if the source on the left sends a packet, then of course you will react by ACKing this packet, which will at the same time ACK this previous one here. If the source code doesn't do it, like if the source sends an ACK and waits for the server to speak. Remember, client server doesn't make any assumption on who speaks and who receives, both can. So there are applications that open a connection and wait for the server to speak. If that happens, this is not compatible with SYN cookies. Question?
So in the SYN cookie, we send the timestamp, but then when we recalculate the cookie later, how do we retrieve the original timestamp?
No, the timestamp is put by the server. It's just to make sure when I receive the cookie back, if the cookie is 3 days old, I will consider the cookie to be invalid. But how do I know it's 3 days old? Well, by the timestamp that I put into the SYN cookie. Voilà, so there are small side effects and the code. So this is an example of why things don't work sometimes on the internet here. Let me skip this and jump to yet another optimization that is also very widespread. It's present in Linux, Windows, Macintosh. It's called TCP Fast Open. It's very similar to SYN cookies, but on the other side, it's here to avoid the problem of that happen when you have multiple opening of TCP connections between the same client and the same server. And that can happen for lots of reasons. But for example, when you do HTTP connections, you transfer something, then you close the connections because you have transferred the file and all the embedded objects. But this will you're connected to the main server, to the same server, and will perhaps in a few more seconds send back another request to the same server. When you do shopping on the internet, those are scenarios where this is very likely to happen. Then the idea here, in a case like this, it's possible to avoid the three-way handshake. One of the problems that companies that are doing servers that do online services would like to solve is the latency. Try to have the interaction with the server seem as instantaneous as possible. Now, TCP requires before doing anything to send a SYN, ACK, and only then send by default. Here we break the default and we allow to send data already in the SYN and the SYN ACK. But in order to do that, we assume we don't do that for the first time. So when this TCP client contacts this TCP server, in the first interaction, the TCP in the previous interaction, the server will send a cookie to this client here. And whenever this TCP client contacts for the second time, for example, the same TCP server, it will send a hash. MAC here sends a message authentication code of the secret server key that was sent previously, and the tag that was sent previously by the server here. Now, when the server receives that, the server will know it's a client that had an interaction with me not so long ago, and will accept to have a different implementation of sockets that allows already to have data in the first SYN packet here. So we will start immediately receiving data, and also to have data in the SYN ACK packet. There is nothing in TCP that forbids that. It's just that the practice for many years was not to do it. A SYN packet is simply a packet that has a bit saying this is the opening of a connection. But you can send data in it. Now, this was not done because people wanted to be careful. Now, the one option that is used is you don't do it at the first interaction, but if you had a recent interaction with a client, you allow this to happen. Voilà, we've seen some highlights of TCPs. I've tried to give, according to my philosophy and other people's philosophy, to go deep into a few details. Tried to give you a number of examples of where you need to optimize a TCP code. This code is being optimized all the time, so there are more and more optimization. Also, some of the optimizations that were done in the past may be modified slightly. For example, the number of duplicate acts we do with fast retransmit tends to be reduced now because networks are reordering much less. But certainly one thing that needs to be added to TCP is security. So TCP was designed in the 70s. The 70s, that was the period des bisounours. The internet was in a world of freaks working in universities. Nobody was, hackers were for fun. The darknet and all that stuff did not exist. So the darknet mafia and so on did not exist. And the computer scientists who did that did not think it would ever exist. They were completely naive. And this has, of course, as soon as the internet went commercial, we had to fix the problem. Today, this is fixed with what is called TLS, Transport Layer Security, which is formally, in the sense of the TCP-IP architecture, is not part of the transport. It's an application framework that comes on top of transport. But most likely, you should today never use TCP without TLS. We'll see an alternative in a few more weeks called QUIC that combines TCP and TLS, or a variant of TCP and TLS in a different way. But for now, in the lab, we will ask you to work on TLS. So what TLS does is adds the two basic functions that are securing an interaction, which are confidentiality, making sure that whoever gets your data, for example, by doing spoofed ARP packet replies in your Wi-Fi access point, or a Wi-Fi access point that is not using any security, then TLS will make sure that this is encrypting using keys that are available only to the two ends, and also authentication, so that will make sure that beyond being able to read what you said, we're also unable to forge any message by mounting what is called a man-in-the-middle attack, which you could easily imagine. If you have access to ARP to forge ARP replies, you can get all the packets that were supposed to be sent to someone else. You get them first, you modify them a bit, and you send them to the intended destination. Man-in-the-middle attack, and this is, you will be able to do that, but it will fail authentication here. Mentioned that already. Many of you know this already. Those who don't know, we will need to make a distinction between symmetric cryptography and asymmetric cryptography. Symmetric cryptography is the most widespread and most efficient cryptography. You have a secret, you somehow shuffle all the bits according to a secret that is used as a key. And we believe if your crypto system is good, which means nobody yet has found a way or published a way to break it. Without the key, it is impossible to recover the message here. That is, the state of the art today is AES, not the state of the art, but the most widespread system is AES, which is still believed to be extremely efficient and very fast. Efficient means the computing times are extremely small. So the overhead of doing AES is minuscule, so we can do it. Asymmetric cryptography is more beautiful. The problem of symmetric cryptography, it requires a shared secret between the two ends. How do I have a shared secret with my bank when I go e-banking? That's, of course, I could require that the bank sends me something that is a long 2000-bit secret that I keep at home and etc. But that's very clumsy, and the bank will need to store all those secrets here. So the problem of symmetric cryptography is the secrets that need to be shared. Also, symmetric cryptography gets old, like all of us and everything on Earth. If you use a crypto system with the same key for millions and millions of messages, then somebody who has copied those millions of messages will be able to gain some information, and it becomes weaker over time. So the AES keys are changed once in a while, after a few seconds or minutes or hours, but you don't keep it for years, hopefully. Asymmetric cryptography is more beautiful because it doesn't force you to share a key. You can have two keys, one that is secret, you keep secret, you don't share it with anybody, and a public key that is derived from this one and you can make public. And the beauty of this, the incredible thing, is that even if your public key is public, you don't lose any secret. And you can, for example, encrypt a message with your private key. Anybody can decrypt it, but by decrypting it, anybody will know that it comes from you. It comes from somebody who has the secret key. So that can be used for authentication and for non-repudiability. In the reverse direction, if you encrypt it with the public key, you know that nobody can decrypt it except the intended recipient. So I can broadcast a message to all of you, encrypt it with a public key of one of you, and only the one of you who is the intended recipient will be able to read what I sent you. That's the beauty of asymmetric cryptography. The problem is that the keys must be very long for this to be safe, and the computing time is not huge, but is orders of magnitude larger than for symmetric cryptography. This is why this is combined in TLS. So this is a very typical interaction. I go to my bank here using TLS. Then I will open a TCP connection. Then I will obtain the public key of the bank. I will verify it. How do I verify a public key? Well, by using the public key of a well-known authority called a certification authority. So we'll verify this. That will guarantee that the public key and the associated material that's written with it has been sent to me by somebody who really is the bank here. And then after that, we will create the session keys, the one used for symmetric cryptographies. That will be renewed. If the session is very long, we will change them once in a while. And then any data that I will send to the bank will be encrypted and will also be authenticated. That's a very simple example. There are other ways, in fact, better ways of combining authentication and encryption here. So if I have a message to send to the bank, I will both encrypt and authenticate the message, so that will prevent man-in-the-middle attack, and that will also make sure that the message cannot be read by illegitimate recipients. So this is the 1-second summary of cryptography for transport layer. Today, when we use secured sockets, we use TLS 1.3 probably, which is the most recent one. It's important in terms of security to always use the most recent security updates because at least today, the state of science in cryptography is that we don't have mathematical proofs that a system is secure, the crypto system is secure. We have mathematical proofs that according to some assumptions in a given attack model, it is secure, but those attack models, those are the ones we think about. So we can prove that a number of attacks are infeasible. We cannot prove that someone knows of another attack, and the NSA probably does. And the bad guys sooner or later will also discover new attacks. So it's a race between the attacks and the defenses. And if you use old cipher suites, so old crypto systems, there is a risk. If they're old, if they've not been updated, it's probably because they're broken. So there are known ways of attacking them. What I said about crypto is a bit naive in the sense I said somebody who doesn't have the secret key cannot decrypt, but this is true if the system is not broken. Now, all systems that are a bit old or that have short keys, there are ways to break them. Some of those ways require massive computing power, but still we should not use them. Because of that, that means that when you cannot simply put into TCP, use RSA and AES with that form key. No, you need to negotiate what systems you're using because this will change all the time. It will change practically every month when you do have an update of your operating system here. So when we use TLS, after we have at the minimum a handshake where, for example, there are many variants in TLS. Here the client says, here are the suites, the crypto systems that I may be able to use, and this will reply. And at the end of that, we will also be able to, as I said before, using the certificates, have the secret keys that we have. So at the very minimum, this uses that. In some cases, it can use more than 2 messages. Only then we can send the data. This is how TCP sockets should be used when they're used with TLS. It's very similar. Sockets try to remain the same. So when we add security, we add minimal changes. Here I'm showing on the left a client, on the right a server. We need to add the things like the certificates. So that must be done by some kind of code. It's called, in crypto system, it's called a context object. Then we create a socket on the server side. We bind, we listen, business as usual. On the client side, we create a socket and then we add security to it by adding, for example, information, which is the certificate that you will use for verifying the other certificates, the certification authority. So this is bootstrap information. This is root information that must be trustable in your computer. Right? It should not come from somewhere else. It should come with your computer. So in practice today, it comes from your operating system. So if you install Linux, if you install Windows or Macintosh, typically it comes first with an operating system version that has such certificates, and then you can update the certificates because you start from some some trust here. If you install Linux, then you have to be careful and know what you do to make sure the thing you get is correct. Once you have that, then it is similar to what we said before. You do a connect that does a SYN, ACK, etc. After this phase here, the server will typically, after this phase here in parallel, the client side will do this security handshake that we said before, which consists in agreeing on the crypto system that you want to use here. And this will be done by this call here on the server side. Once this is done, things are as before. You do send and receive. If you use all this, which is probably what we do today whenever we go to any website, I mean, if you try with a modern web browser to go to a website that's not using TLS, you will probably receive an error message asking you, are you sure you really want to go there? This is not secure. Being not secured may mean what? What can happen if you go to a website, if you use TCP without TLS? Yes? There is no content guarantee, which means the message you're receiving from your bank or from someone else might be wrong. For example, you want to buy a ticket and they say, no, those tickets are not for sale. In fact, it's wrong. It has been forged by someone else who wants to prevent the rest of the world from buying tickets, for example. Yes, exactly. Yes? Data is sent and?
Data is sent, you believe you send it to the server.
You believe you send it to the server and you send them to someone else. Exactly. Yes, exactly. So this is the man-in-the-middle attack is possible. Man in the middle might give you a wrong answer or might also get your information to impersonate you, which means, for example, you're transferring from your bank some amount of money to me, for example, but the man in the middle changes the destination and sends to someone else. So you believe you've paid your bill, but in fact, you've not paid your bill, you've sent the money to someone else. So of course, you don't want to do this, and in reality, you don't do it today. So you use HTTP TLS. Now, the price to pay is how much in terms of round-trip times. That's the question of this quiz.
This is for first connection?
Yes. I close the poll in a few seconds. Closing. Majority says C, which is perhaps true. I'm not too sure, but the minimum is 2. Let's see why. You need at least to do this. Now, of course, there is that, which is a fraction of round-trip time. And then you need also to do the crypto handshake. So you have all those messages that must be sent. So it lasts at least 2 RTTs, a bit more, in fact. So 3 RTTs is perhaps also a correct answer. And that's exactly the problem of today's TCP. TCP requires TLS, and TLS plus TCP requires 2 round-trip times. So before you click on the page, and before you in fact get anything, you have to do all that stuff here. So the latency of TCP is very large. Yes, question?
Why can you not send the client call in the same?
Well, if you do that, you do exactly what we call quick. So right now we do first TCP. I mean, the way the operating system implements and the standard says TCP is, you do that first. And once you have a TCP connection, because TLS is an application layer protocol, so it uses sockets also. I showed the TLS sockets, but this is a classes that wraps around the true socket. So the way it's designed is like this. And you're right, why not do it? And this leads to another system, which is called Quick. So Quick will do it differently. We'll first do the security association, and only then, if that succeeds, we'll transfer data. And of course, the SYN packet and everything can be piggybacked with the security association. Quick has a number of other aspects that we will discover a bit later. I'll skip the rest of this transport layer module. The part that I'm skipping is on the optimal performance. So it's interesting if you're interested in performance, but it's not critical to understand how it works. So I will simply post it and post the solutions. Instead, we will directly move to the next chapter, which is the multicast. So without much transition, we switch topic, we return to the IP layer, and we discuss more on something that we've encountered many times, in particular because of IPv6, that is very fond of using lots of multicast addresses. And that is illustrated on this, not on this, on this front page. This is an error message I got a few years ago when I was listening to a French radio sender on the internet. And then it says, I've observed that you keep your connection long with us. It costs us a lot of money to maintain all those servers for you to listen to our radio. Therefore, we time you out. Sorry. Because obviously they are not using multicast. Motivation of multicast was exactly to be able to broadcast to a large audience the same content. So a football match, a live TV news bulletin, for example, finance information from the stock market, games, when multiplayer games, when you want to send the same information to a number of people. You can always do that at the application layer. You can send the information to a replication server where I send the video or the image to one server and the server sends it to everyone. This is what is done by many, but not all. And if you do that, of course, the server time, if you have 1 million receivers, you have one server that sends the same content to 1 million receivers with 1 million TCP connections, perhaps, and 1 million buffers and 1 million everything. So the motivation of multicast is to save on the server side. With multicast, a server that needs to reach 1 million destination will send only one packet. This is associated with special addresses that we've seen already. With IPv4, those are the addresses that start with 224 and above. And with IPv6, those that start with FF and the rest, anything here. An IP multicast address has nothing to do with the regular IP address. It is a logical address of a group. We've seen that when we saw, for example, that when an IP host starts and wants to acquire an IPv6 address, it might send a message to all routers in the local area. So there is a multicast address, which means all routers on all on-link routers. So it doesn't say which router it is. It's just a logical name associated with whoever believes they are a router. Here, the original intention was also to use, for example, to identify TV or radio channels. The idea of multicast was, in the 70s, 80s, people thought that radio systems would come, but radio bandwidth is limited, and therefore it's better to use the internet for sending, for broadcasting systems instead of using the radio waves. Well, we still use radio waves for broadcasting audio and video content, but that was the idea. So this identifies a channel. So an IP multicast address is used to identify a group. In fact, there are two ways of doing it, which are called any source or source specific. Any source multicast means this IP address can be used by anybody to send to. So there can be multiple sources. Source specific means, and the group is therefore identified fully by the address. Source specific means, no, this group, this multicast address is not saying what the group is. The group is the combination of a specific source and this address. Or another way to view it is when we use source specific multicast, we're identifying explicitly the source. So in a source specific multicast group, there can be only one sender, which is more in line with the system of audio and video broadcasting. The difference between the two is in different ranges here in IPv6. Those are the ranges that correspond to source-specific multicast. In IPv6, this is the range here. As we will see, source-specific multicast is much simpler, but came a bit after. How does it work? Well, here is the basic slide that explains, at least as a first approximation, most of the content. Say S, which is a video server, has some information to send. S does not know whether somebody is listening or not. It simply sends to a multicast address. So in order to send, you simply create a packet using socket. Then you find some way to say to your socket, the destination address is M, and M is a given logical group, is a multicast address. Of course, you do that over UDP, because multicast doesn't work with TCP. Why? Well, with TCP, you require ACKs. I send a packet, I want to be acknowledged. If I have 1 million destinations, what do I do with 1 million ACKs, right? It probably defeats the purpose of multicast. You can do reliable multicast, but then it's a completely different story that we won't cover in this course. You need to add coding mechanism. You add parity, messages, and so on. So most of the systems we will see are non-reliable, or they use reliability from the application layer, for example, with video encodings at different resolutions. We will not discuss here. So we have a UDP socket, and we simply send to M. Here, assume nobody's listening. So you're alone in the world, you send a multicast packet, nobody listens, which is perfectly legitimate. Remember the example I gave, a host boots and wants to know, is there a router on link? Well, if there's no router, nobody will answer. So what can happen? And that's it. Now, assume that somebody wants to listen, A wants to listen, then in order to receive data from a multicast group, except if you're on link, but if you want the data to come via routers, you need to inform the routers that you want to receive. It's not done by default. That's the opposite of unicast routing. Right? I know that I will be reached by the router because I have put the correct prefix in my address, and the router therefore will send it to me. For multicast, there's no concept of prefix. The addresses are purely logical. I need to send a message, so I need to join here. So in the socket, if I want to receive, I need to say, I want to receive the data. It's a subscription. A multicast socket must subscribe to receive things. By subscribing to the group, here I'm assuming this is a source-specific group. So I want to receive the data to this multicast address sent by source M. And I give the information to the router. This is the protocol called MLD, Multicast Listener Discovery, or IGMP, Internet Group Management Protocol. That's for IPv4, that's for IPv6. It's like ARP. They're doing exactly the same thing, but when it's IPv4, IPv6, they have different names. Many people will call it IGMP because it was there before. So that's between host and routers. If you want to receive something, you have to send an IGMP message. Then there is a magic that will happen in the network, which is called multicast routing, that we will discuss next week, that causes all the routers to create a tree in the router. So this red information is here saying to router R1 is saying there is somebody on the left port that is subscribing to M. And then R1 must talk to R2 using a routing protocol, so a language, a protocol that's between routers, one that we see only if we do Wireshark, otherwise it's never visible to end users. But R1 will say, there is somebody here, so please remember that there is somebody, and you must send to me all the things for the group SM. R2 will do the same here, so they build what is called the multicast distribution tree. And now, when S sends a packet, R5 knows it has to send it to R2, to R1, and R1 will send it over this local area network, over the switches, in which A. Assume B, sooner or later, also does the same thing. Then R4 will also remember. And R4 will talk to R2 and say, now I need also to receive it. And that's the end because R2 already has some state information for this flow. R2 already receives data that goes to group SM. Therefore, that's the end. R2 knows how to do that. But now R2 must remember that when it has a packet that comes here, it must duplicate it to R1 and to R4. The duplication of packets is done by the routers here. This is why it's good for sources, but this is why it's bad for routers. Is it a good idea or a bad idea to do that, to put the work on routers rather than sources? Well, it's a bad idea to put on routers because routers are real-time fragile machines that are critical. The servers are a bit less critical. But it is still a good idea because of this exponential thing. If I ask a router to do just one single duplication, it's a small word. You have one packet, you create 2 copies, right? If you do that 10 times in sequence, at the end, how many copies do you have? Well, you have 1,000 copies, right? If you do it 20 times, you have 1 million copies. So by duplicating a number of times, at the end, you have an exponential number of things. So by having the routers in the network duplicate, after all, that's the history of all big organizations. An army is made of a general, or in Switzerland, a colonel, and so every level has a small number of people below to whom they repeat the orders, and at the end, we reach millions of soldiers. So that's the same idea. This exponential growth of the multiplication is the motivation for multicast here. Instead of having the source create 1 million copies, you will have perhaps 20 routers on the path at which each will duplicate or multiply a number of copies. Voila, that's all we will do for today. Next week, we will speak of routing for multicast and also for the more standard cases.